180 tons of liquid oxygen and kerosene detonated with the force of a 1-kiloton bomb, vaporizing a launch pad and everyone standing within 100 meters of it. That was not a weapon test. That was a rocket simply trying to lift off. The line between a controlled launch and an unplanned explosion is terrifyingly thin, measured in milliseconds of valve timing and millimeters of turbine blade clearance. When you stack thousands of tons of volatile propellants into a machine the size of a skyscraper and light a match underneath it, you are not just fighting gravity. You are fighting combustion instability, pogo oscillations, guidance system drift, and the brutal reality that any single point of failure can turn a multi-billion-dollar vehicle into a fireball before it clears the tower. What does it feel like to be the flight controller watching the telemetry flatline while the ground shakes beneath your feet? What goes through a designer's mind when years of work collapse into a column of black smoke on national television? Today, 9 rockets that never made it past the launch pad. Before we start, tell me in the comments where you're watching from and subscribe so you don't miss which failure takes the #1 spot. N-1 Soviet moon rocket. By 1967, the race to the moon was a sprint. The Soviet answer to the American Saturn V was this, a 105-meter-tall monster with 30 engines clustered on its first stage. The N-1 was designed to throw 95 tons into low Earth orbit, but it never flew for more than 2 minutes. The core flaw was not a single bad part, but an engineering impossibility, controlling 30 rocket engines simultaneously with 1960s analog computers. The Block A first stage packed those 30 NK-15 engines into a ring, generating 45 meganewtons of thrust. To steer, the KORD computer had to shut down engines opposite any failure to keep the rocket balanced. This worked on paper. In reality, the plumbing feeding kerosene and liquid oxygen to 30 engines was a nightmare of pipes, valves, and pumps. Vibrations from 29 engines shook the 30th apart. A single faulty pump could send a pressure wave back through the fuel lines, starving other engines and triggering a cascade of shutdowns. The cord computer, overwhelmed, would then kill healthy engines to compensate, leaving the rocket with too little thrust to climb. The first launch in February 1969 lasted 68 seconds. A fire in the tail section caused the cord to shut down 29 of the 30 engines. The rocket fell back to the step. The second launch, on July 3, 1969, was worse. At liftoff, a loose bolt was sucked into an oxygen pump, destroying the engine. The cord shut down 29 engines again, but this time the rocket had barely cleared the tower. It fell back onto the launch pad, detonating nearly 2,000 tons of kerosene and liquid oxygen in one of the largest artificial, non-nuclear explosions in history. The blast obliterated the launch complex, leaving a crater and putting the pad out of commission for 18 months. The program limped on with 2 more failures before cancellation in 1976. The Soviet moon rocket never left the atmosphere. Vanguard TV3, December 6, 1957. The Soviet Union had already orbited 2 Sputniks. This was America's answer, broadcast live to the world from Cape Canaveral. The countdown hit 0. The first stage X-405 engine ignited. The rocket rose about 4 feet. Then it stopped. For a brief, terrible moment, the 72-foot vehicle hung motionless before settling back onto the launch pad. The fuel tanks ruptured, and the entire rocket vanished in a boiling black and orange fireball. The tiny satellite was thrown clear, its transmitters still beeping uselessly from the ground. The failure came down to a catastrophic pressure drop in the propellant feed system. The X-405 engine used a turbo pump to force fuel and oxidizer into the combustion chamber, but during startup, the tank pressure was slightly lower than nominal. This allowed the burning gas inside the chamber to push backward through the injector head before full propellant flow was established. A pressure spike blew through the injector rings, burning them out completely. At T+1 second, a shock wave ruptured a fuel line, and the engine lost all thrust. The rocket had no fins for aerodynamic stability. It relied entirely on gimbaled engine nozzles for steering. With 0 thrust, it was a dead weight, balanced on a column of fire that no longer existed. Gravity took over. Newspapers called it Flopnik, Kaputnik, Stayputnik. A Soviet delegate at the UN offered American aid reserved for undeveloped countries. The Vanguard satellite now sits in the Smithsonian, a polished aluminum sphere that never reached orbit. Europa 1F-9, November 1968, the Woomera launch site in the South Australian desert. The Europa 1 rocket stood on the pad, a 3-stage vehicle built by a coalition of European nations. The first stage was the British Blue Streak, a converted ballistic missile. The second stage was the French Coralie. The third stage was the German Astris. The F9 mission was supposed to be the first full test of all three stages working together. It never left the ground. During the final fueling sequence, the Astris third stage exploded. The blast ripped apart the upper portion of the rocket and scattered debris across the desert floor. The Astris stage used a pressure-fed engine system. Nitrogen gas pressurized the propellant tanks to force fuel and oxidizer into the combustion chamber. The investigation pointed to a catastrophic overpressurization. A valve in the pressurization system likely failed closed. The nitrogen gas had nowhere to go. The tank pressure spiked beyond the structural limits of the aluminum alloy walls. The tank burst. The hypergolic propellants, which ignite on contact, mixed instantly and detonated. Hypergolics are efficient but unforgiving. No ignition system is needed, which simplifies engine design. But any leak or structural failure that brings fuel and oxidizer together means an immediate, violent reaction. There is no abort sequence fast enough to stop it. The explosion on F9 was not a launch failure. It was a ground handling failure, a plumbing problem that turned a fueling operation into a wrecking operation. The Europa program had already suffered multiple partial failures in earlier test flights. This was the moment the structural fragility of the design became undeniable. The rocket destroyed itself before the countdown even reached 0. The F9 debris was never recovered for a full reconstruction. The program limped on for a few more years, but never achieved a successful orbital launch. The final Europa flight failed in 1971, and the project was canceled shortly after. But Atlas Able 9A, the Pioneer P, 3 lunar orbiter mission, September 1959. NASA needed a deep space capability, so Convair stacked an Able second stage and a solid fuel Altair third stage atop an Atlas D first stage. Total height, around 27 meters. Payload to translunar trajectory, 180 kilograms. The Atlas first stage was a stage-and-a-half design. All 3 kerosene and liquid oxygen engines ignited on the pad. 2 booster engines would shut down and be jettisoned mid-flight, while the central sustainer engine burned all the way to orbit. The vehicle was never supposed to leave the ground during this test. It was a static firing, a full-duration burn with a rocket bolted firmly to Launch Complex 13 at Cape Canaveral. Engineers wanted to verify that the modified Atlas could handle the structural load of the upper stages before committing to a real launch. The problem was the thin stainless steel tanks. Atlas relied on internal pressurization for rigidity, a technique called balloon tank construction. Tank walls were as thin as 0.25 millimeters in places, barely thicker than a soda can. Without constant nitrogen pressurization, even an unfueled Atlas would crumple under its own weight. During the static fire, something breached that delicate pressure balance. A leak, a structural buckle. The exact root cause was never made public, but the result was instantaneous. The entire vehicle lost structural integrity, while all 3 main engines were screaming at full thrust on the pad. The rocket collapsed into its own fireball, and the Pioneer P3 spacecraft, a 168-kilogram aluminum sphere packed with a radiation counter, a plasma probe, and a micrometeoroid detector, was vaporized before it had any chance to get to the moon. Launch Complex 13 suffered severe damage. Equipment was shredded, gantries warped. The program's first Atlas Able had already blown up during a static firing months earlier. This was the second. 0 out of 4 operational Atlas Able launches ever reached orbit. Ariane 5 Flight 501, June 4, 1996. The European Space Agency's brand new heavy-lift rocket stands on the pad in French Guiana. It carries 4 cluster satellites, a 1.2-ton scientific payload designed to fly in formation and study Earth's magnetosphere. The mission cost exceeds $370 million. 37 seconds after liftoff, the rocket veers violently off course and self-destructs. The debris rains into the Atlantic. The cause is not a faulty weld or a leaking fuel line. It is a software bug. A single line of code, ported directly from the successful Ariane 4, kills the Ariane 5. The inertial reference system, the computer that tells the rocket which way is up, runs a routine called alignment. On the Ariane 4, this routine stayed active for about 40 seconds after launch. On the Ariane 5, it serves no purpose once the rocket leaves the pad, but nobody deactivated it. During the climb, the Ariane 5 accelerates horizontally much faster than its predecessor. A variable measuring horizontal bias suddenly balloons to a value that does not fit inside a 16-bit integer. The software tries to cram a 64-bit floating point number into that tiny space. It overflows. The computer throws an exception. The programmers had deliberately left this specific variable unprotected to keep the processor workload below 80%. They assumed the Ariane 4's flight limits still applied. They were wrong. The exception shuts down the entire guidance unit. Then, because the redundant backup runs identical software, it shuts down too. The dead computer spits out a diagnostic bit pattern. The main flight computer misinterprets this garbage as valid steering commands. It slams the engine nozzles full over. The rocket pitches sideways, exceeding a 20-degree angle of attack. Aerodynamic forces rip the solid boosters from the core stage. The automated flight termination system triggers. The inquiry board later noted a fundamental assumption that software should be considered correct until proven faulty. For replacement cluster, 2 satellites eventually launched aboard Soyuz rockets in 2000. The Ariane 5 went on to become a workhorse, but its first flight remains one of the most expensive debugging sessions in history. Titan 34D-9. April 18, 1986, Vandenberg Air Force Base. The payload is a KH-9 hexagon spy satellite, the last of its kind. At T plus 6 seconds, the right solid rocket motor ruptures. The left motor, torqued by the asymmetric thrust, breaks free and triggers its own automatic destruct system. The core stage blows apart, rupturing the second stage's oxidizer tank. The upper stages and the satellite are hurled into the air. At T plus 20 seconds, the range safety officer sends a manual destruct command. The KH-9's internal self-destruct mechanism also fires, shredding its classified film reels into hundreds of pieces. A cloud of toxic hydrazine and nitrogen tetroxide settles over the launch complex. Debris rains down, starting fires that burn for 2 days. Personnel are trapped in the blockhouse by the fumes and flaming wreckage. The right solid rocket motor, largely intact, crashes down onto a concrete structure near the pad. The root cause was a small air pocket between the solid propellant and the metal motor casing. Hot exhaust gases burned through the casing wall, a process akin to a blowtorch cutting through steel until the motor burst. The manufacturer, Chemical Systems Division, had let quality control lapse. The booster segments were at least 5 years old, and the production line had been shut down since 1982. The Air Force, before the investigation concluded, was so baffled by the back-to-back Titan failures that it suspected sabotage and had personnel comb the hills around the base for bullet casings. The launch complex was out of commission for over a year. The remains of the KH-9 were buried in an undisclosed location in Nevada. Nedelin Catastrophe R-16, October 24, 1960, Pad 41 at the Baikonur Cosmodrome. A prototype R-16 intercontinental ballistic missile stood fully fueled, undergoing final checks. The missile was over 30 meters tall, weighed 141 tons, and was loaded with a hypergolic fuel pair, UDMH, and a nitric acid solution nicknamed Devil's Venom. Hypergolic means the two substances ignite violently on contact, no spark needed. This made the missile simpler to store and launch than earlier rockets using liquid oxygen, but it also meant any leak or premature mixing inside the plumbing was an immediate, unstoppable catastrophe. The oxidizer was so corrosive, it could eat through metal and human flesh with equal ease. On this day, schedule pressure was crushing. Marshal Mitrofan Nedelin, head of the program, was personally present, pushing to launch before the November 7th anniversary of the Bolshevik Revolution. Safety protocols collapsed. Technicians were troubleshooting a faulty sequencer, while dozens of personnel stood around the fully fueled missile, not in bunkers. An erroneous electrical command from the repaired sequencer fired the second stage engine. The engine's exhaust blasted directly into the first stage below, rupturing its tanks. The hypergolic propellants mixed and detonated instantly. People near the rocket were incinerated. Those farther away were trapped by a barbed wire security fence and engulfed in a fireball of burning, toxic fuel. Marshal Nedelin, his top aide, the USSR's chief missile guidance designer, and over 70 other officers and engineers died on the spot. Chief designer Mikhail Yangel survived only because he had walked a few hundred meters away to smoke a cigarette. The official death toll was suppressed for decades, with the government claiming Nedelin died in a plane crash. A 1994 state commission finally confirmed 78 dead, though estimates range up to 126. It remains the deadliest Launchpad accident in history. VLS-1VO3, August 22, 2003, 3 days before its scheduled liftoff from the Alcântara Launch Center in Brazil. The mission aimed to orbit 2 small satellites, but the rocket never left the pad. The core flaw was a catastrophic, unplanned ignition of a first-stage solid rocket booster. While the vehicle was still firmly clamped to its launch table, surrounded by an unretracted mobile integration tower packed with personnel. Solid rocket motors are essentially giant tubes of pre-mixed fuel and oxidizer. Once lit, they cannot be throttled or shut down. They burn at full fury until the propellant is exhausted. On the VLS-1, 4 of these boosters were strapped around the central core. When one booster's motor fired spontaneously, its exhaust plume, superheated to around 3,000 degrees Celsius, blasted directly into the adjacent boosters and the fully fueled upper stages. The thermal assault triggered a near instantaneous chain ignition of the entire vehicle stack. The rocket did not lift off. It detonated in place, converting the launch platform into a stationary fireball. The mobile integration tower stood enveloped in that inferno for 5 minutes before collapsing. 21 civilian technicians and engineers, spread across its 5 floors, had no time to escape. The official investigations, conducted jointly by Brazilian and Russian experts, pointed to an electrostatic discharge as the most probable culprit, a spark jumping inside the detonator circuitry of the A booster. A mechanical safety lock that could have prevented the discharge had been removed from the design after an earlier ignition failure on the program's first flight. The investigation noted that the device was absent, but did not assign it as the definitive cause of the accident. The detonators themselves had been installed 2 days ahead of schedule by the technical team, a procedural deviation that placed a live rocket in a vulnerable state while work continued around it. The Brazilian space program was set back by years. The VLS-1 project was ultimately canceled in 2016, and its partially built 4th vehicle was scrapped. Delta III rocket explosion, Flight 259, August 26, 1998, Cape Canaveral, Florida. The maiden flight of Boeing's new Delta III rocket carrying a Galaxy 10 communications satellite. The vehicle lifted off, began its roll program, and then 71 seconds into the flight, the range safety officer sent the destruct command. The rocket and its payload, a total loss of over $225 million, fell into the Atlantic Ocean. The root cause was a guidance system fighting itself to death. The Delta III was a stretched, upgraded Delta II, but its control software was largely carried over from its smaller predecessor. The problem was roll control. The first stage had 2 small Vernier engines and 6 ground-lit, solid rocket boosters, 3 of which had vectoring nozzles. The flight control system used a simple roll control logic. When the rocket began to roll, the system commanded a correction, but the aerodynamic forces on the larger 4-meter diameter vehicle were completely different from the narrower Delta II. The control system's gains were set too high. A small roll oscillation started. The software, tuned for a less responsive rocket, overcorrected. This induced a larger oscillation in the opposite direction. The system overcorrected again. Within seconds, the roll oscillations grew from a wobble into a violent, uncontrolled corkscrew. The aerodynamic stress on the accelerating rocket became immense. The solid rocket boosters, attached to a structure designed for axial thrust, were subjected to severe lateral loads they were never meant to handle. The hydraulic actuators for the vectoring nozzles depleted their fluid reserves, trying to keep up with the insane commands from the flight computer. The rocket was tearing itself apart. The destruct signal was sent, but the vehicle had already begun to disintegrate. The telemetry data later showed the roll rate had reached several cycles per second before the signal was even transmitted. Boeing engineers had destroyed their own rocket on its first flight because of a fundamental mismatch between an old brain and a new body. Engineering tolerances are unforgiving when gravity meets combustion at the pad. If you enjoyed this video, leave a like and subscribe to the channel. Drop your idea for the next episode in the comments.